Okay, hi everyone, and welcome back to this part 2 of this framework of memory for learning. So last week we talked about like how memory can be used as abstraction, and also like how we can use like a lookup table to match some like existing state to memory using some attention-based metric. Okay, but today we'll just be going through more of an application of this memory. So fundamentally, I'm interested in reinforcement learning, like how humans learn so fast and can adapt well to different situations. And I find that there's a big gap right now in current reinforcement learning systems because it learns very slowly, typically requiring millions of time steps in order to learn something. And so there must be something that can make it more efficient. And I think the answer actually lies in how we utilize memory, how we store memory, and how we use this to new situations. So let's just begin. So memory in reinforcement and continual learning. Okay, it's not just important to do like reinforcement learning in a fixed environment, like for chess or Go. I mean, those are important ideas where you can have optimal solutions by AI repeatedly playing against itself in the same environment. What I'm interested in is actually whether the AI can adapt to new situations. Like if you are doing a navigation robot, if you suddenly add an obstacle, can the robot learn to maneuver away from it? Self-driving cars, if the road suddenly changes, can the self-driving car adapt? So this kind of things are the kind of problems I like to solve. And so let's just touch on typical reinforcement learning here. Can I just check how many of y'all are like familiar with reinforcement learning? Okay, or not so? Okay, if you are familiar, maybe just give a hands up. Okay. All right. So I would say roughly familiar. Okay, so let me just briefly describe, okay, what is a reinforcement learning cycle. So a reinforcement learning cycle is like this. Typically, you have this thing called the value function or your reward. So you typically have a reward. And then if let's say if you have a reward like that's high, like maybe a reward of 1, that means this action is like a good action. You want to repeat it. Good set of actions. Yeah. But if your reward is like low, like maybe, I don't know, in another environment, you could have reward of like -1 or 0. That means it's like you don't really want to repeat. Yeah, so it can be done for like a single action or like a set of action, a sequence of actions. And so reinforcement learning basically means that like when given a reward, like if, for example, you do an action that is, think of a child, okay, you want to reward the child for like good behavior. So if the child displays the good behavior, you give him a cookie. If the child does not display good behavior, you scold him or her. Yeah, so something like that. That's the like basis of reinforcement learning, where you reinforce based on a reward signal. Okay, but I would like to argue for the case that using this reward is a very slow process. Okay, let me just explain why. Okay, this can be very this can be quite new for a lot of people because everyone talks about rewards for reinforcement learning. But let me just show you why rewards can be inefficient. Okay, this is how we normally update rewards, like in a tabular case, a value function for the like a value function like that, you update with the current reward for the time step plus the future expected reward. Okay, minus away the current reward. So this is like the difference between, okay, the difference between your prediction, or rather this is your actual one step look ahead versus predicted. Yeah, so you try to bring your predicted value closer to the one step look ahead value. So in so doing, like if let's say you have like, let's say a series of states like this, like state 1 goes to state 2, goes to state 3, and so on. Like eventually, like if you have the reward here as 1, you want to bring the one step look ahead here closer to this value here. This one would be like very close to it, like 0.99. And then after that, like you can even go up here to 0.98 and so on. So you can actually update your value of your states such that this path, okay, becomes the preferred path to choose. Okay, just by doing this update equation, by predicting each state as the like discounted sum of the next state. Same thing for the Q value. Q value is you do a state and action pair instead of just a state value. So you also have the predicted target, the actual minus the predicted. Okay, so this is basically how we update the value function. And basically you can see there's a problem here. Okay, I mean it will work if there's very few states, right? But let's say if we like, let's look at the word maze here. Like, let's say this is our series of states that we want to do. Like, you start from the agent here and you move to the door. You can see that this is the, like, probably the fastest way to reach the door. However, there's a problem if you use value methods. Okay, if you use value method, imagine only the door is a time step of a value of 1. Okay, so in order for this equation to update, you need to transit this path here. So it means that on the maybe like the first iteration through, I get my value function as here as 1. Okay, then the next cycle I solve it, I can update this one as 0.99. Okay, then the next time I solve it, I update this as 0.98, discounted of the first one. And then you can see that it takes exactly like 1 transition like that in order to update it, because you need to update it backwards. So you will need to like update it. Oh, I just erased it. Okay, but basically you just need to update it. Like every time you update is like 1 episode, unless you do some form of replay. Okay, so this is very inefficient, right? Can you see that the number of squares you need to update is basically proportional to the number of episodes you need to run? So I mean, it's no wonder why like reinforcement learning agents learning how to walk will need like millions or billions of time steps. It's understandable, because if you want to back propagate this value function from like the good state all the way to the back, you will need a lot of updates. Okay, and these updates typically takes as many updates as your path length. Okay, and it's very inefficient. So this is why traditional reinforcement learning methods with like the value functions are typically not very fast to adapt to new situations. Okay, I mean, sure, you can use this.
Changmin, yeah. Can I ask a question? So even though it takes a long time to converge, it's still very good, right?
You will get the optimal set of results.
I mean, the performance is good if you have the enough time for training, right?
Correct. So there's no doubt, like in like AlphaGo or like in recent works, I guess if you look at like Cicero or something, I mean, if you use some form of reinforcement learning, like PPO is the policy gradient method, the proximal policy optimization. Those methods actually work pretty well for a fixed environment, because you have enough time to train on it. You will get more or less the optimal way to do it. Yeah, so there's some merit to using this kind of value-based methods. It's just very slow to learn. Yeah, probably did I answer the question?
Oh, yeah, that was great. No, yeah, that was perfect. Actually, I'm curious, just to sort of pick your brain on something. So if you is the learning in this happening in a progressive way, or is it more like phase transition, meaning that you don't learn for a long time and suddenly you can do really well? Or is there a progressive improvement? Let's say I stopped the training, I stopped the learning, halfway or something. Is like, have I learned enough about the environment to interact with it? Let's say not optimally, but good enough?
It depends on how long you've trained for, because like, let's say in this case, if you only have learned to do the value, because the value propagation typically works backwards from the state of like the goal state. So let's say you only learn until here.
Yeah.
Okay, so all these are like the optimal states already. If you reach here, you can reach the goal. Okay. But you may not have an idea how to like solve this first part here, because you haven't learned how to solve this yet. So unless you start off somewhere here, if not, you are going to have very spurious performance.
Okay, cool, thanks.
Yeah, so that's why reinforcement learning, usually people train for millions of time steps, because you need to backpropagate all these values all the way to the start. Yeah. So actually you can tell that I'm not very happy with the current reinforcement learning methods. I mean, they have been useful, but they don't look like they can learn in real world situations. I mean, maybe useful for very like simulated or very fixed and narrow environments. So there's one idea that I got very interested in. It's called the Hippocampal Replay. So in my Neurips workshop paper, I actually was working on this Hippocampal Replay. And typically I was trying to model this part here. Like you can see that the rat, when it moves like from this orange circle to this blue circle, it kind of like, while it's moving, it kind of replays the states from the first state all the way until the current state. And then it back replays, or the reverse replay from the current state to the start. So there must be some use of this method. Okay, and in the Neurips paper, I I didn't do this part, which is like the forward prediction part, okay, because I didn't know how to do it yet. Okay, but in this today I actually have figured out a method to use this part also. So it's quite cool. You can actually do this backwards part and the forward part exactly like how the biological system works. So it's quite cool because I think that like there's some reason why this is done in the hippocampus, and I'm trying to see like whether or not we can encode it out in the algorithms. So I mean, just talking about this earlier part here, what we can do is we can basically do like retrieve the successful trajectory, and then we can update the successful trajectory. So early on, what I was thinking is when we update the successful trajectory, we can back propagate the rewards one by one. Okay, remember the earlier slide of the grid wall? So with this hippocampal replay, when you actually succeed in solving the environment once, you can actually backpropagate the rewards one by one until you reach the start state. So you can always solve it. So something like this. So that will be very like interesting because you can then solve. So like the moment you have solved this, you can solve it forever. Okay, of course, in the paper, I didn't exactly use a reward-based method to propagate. I actually did some form of basically exploit, and I just set the exploration parameter to 0 in order to like encourage. Okay, later there's a slide on that. Yeah, so I realized that after I went to Neurips, I realized that whatever I was thinking of is wrong. So I'm actually proud to admit that my Neurips workshop paper, I don't think is the correct way to do it. Okay, because I found a better approach. And I'd like to just emphasize that this replay buffer backwards is different from like the main methods in deep reinforcement learning, like the random sampling of replay buffer in deep Q networks, as well as like prioritized experience replay. This one are all different because they don't exactly sample the states backwards. So this is like how this was done in the workshop paper. So what I did was basically I ensured that there's always a high value path over here. So when I do like exploit based on a count-based system, okay, you will always choose like the exploit path. And then if let's say you have this state as the exploit path, you can actually sometimes also move here because I put the number of moves as a parameter also. So it will prioritize states that have a higher move count. So you can actually like sort of improve a little bit with hippocampal replay. Okay, but I'm not going to go through too much on this. If you are interested in this, you can actually look at the previous YouTube videos I posted on this. Yeah, but I'd like to say that I don't think this is the right approach now. Okay, and I'd like to emphasize more on what I think is the correct approach for this hippocampal replay. So before we go on, let's just do like a quick thought about like how we model the world. Okay, so there's this new trend in reinforcement learning called world models. Okay, actually it's not a new trend. I mean, back in the days of like the Dyna, the Planner, all this, they also tried to plan based on predicting the future states of the world. So some notable works that use world models are like mu0, where you try to learn the Markov Decision Process of the world, as well as Dreamer v2, where they try to predict the next state of an Atari game. Okay, but there's some problems with this world models method. Okay, number one, and the most important is that they actually take a very long time to learn. Like mu0 takes much longer than alpha0 to learn, and alpha0 is already taking like weeks. Okay, I mean, if they say the 4 TPUs method is taking 1 day, mu0 will probably take more than 1 day. Okay, I don't know how long it actually takes, but it definitely will take longer because you need to learn the world model as well. Okay, Dreamer v2, they also didn't say how long they take to train. I suspect it's a few weeks. Okay, so this is actually quite impractical because like if you want to model the future state of the world, it takes so long to train. Imagine what happens if the world suddenly changes. Then you need another few more weeks to train, right? So that's not very practical on a real life robot. Okay, so I'm actually not too keen to like do model prediction of the world, okay, contrary to popular methods, because I feel like it would take too long to calculate. Okay, later I can show you some experiments I did on this. The amount of time it took to model the future state prediction of like the maze world is like easily 6 or 7 times more than just predicting the action itself. So this is actually true. This is definitely true. Okay. Also, if we were to talk about probabilistic methods, so like for a state here, state 1, you have a 50% chance of going to state 3, and you have like a 50% chance of going to state 2. Okay, of course, in order to do this, like if you want to do the world model, you need to actually model your probability of transition, which means what? Which means you need to sample a lot of transitions from state 1 to state 2, state 1 to state 3. So like you sample one state 1 to state 2, you sample another state 1 to state 3, And then you need to sample a lot of these transitions in order to form an accurate probability estimation. Okay, so this is actually needed if you want to do optimal prediction. Okay, if you want to do optimal, this is needed for optimality. Okay, but however, there's some problems with this. You know, when you do this kind of probability transition, firstly, you need to know what are the possible future states. Sometimes the future states are unbounded. Okay, like especially for those like continuous state spaces, the next state you can go to can be like potentially unlimited. And how are you going to get all these probability values? Okay, and also if we want to talk about like multi-agent systems, they may not follow the Markov decision process as well, because this state probabilities actually depends on your agents. Also, this is actually depends on other agents. So I'm just saying that modeling probability like that may be infeasible. So I'm proposing we do away with this modeling of probabilities. So that's the next slide. So this is the proposed new RL framework that I was thinking of. So don't model Markov decision process because it takes very long to do the probability estimations, as well as if you have unbounded state and action spaces, it's almost impossible to get probabilities anyway. Okay, there's always this problem of intractability of probabilities. That's why we have to use approximation methods like Markov chain, Monte Carlo, or like you have to use the elbow, the variational loss as a lower bound. Those kind of things are actually implemented because there's a problem with actually evaluating probability in complex spaces. Okay, so I'm proposing we don't even need to do this. Okay, how do we do RL then if we don't model the probabilities? Okay, we actually just need to store the next state in memory. So as long as you form something like this, a key value table, you can then reference this key value table, and then you can sort of approximate your probabilities by doing sample counting. Okay, so this is something that is actually quite intuitive. Okay, but of course, you need a lot of samples in order to get optimality. So I cannot promise optimality with this method, but it is definitely much faster if you think about it. Okay, so what I'm proposing is that actually most short-term transitions can be deterministic. So maybe we don't even need to model these probabilities here. Okay, because like you only transit to one state. Like when I actually walk forward, I don't expect to like 50% of the time I walk forward, 50% of the time I walk backwards. So that's not exactly like how the world works, right? But in RL environments, sometimes they introduce stochasticity in the actions, which I think can be quite unrealistic. So this is something that I think we can do away, because adding stochasticity in the environment is just artificial. And although it can actually help with the current methods, because current methods take so long to learn already, adding stochasticity is fine because it still takes very long to learn, and it can guarantee convergence to optimality, because when you do enough trials, you get the right probabilities, you can then do optimal prediction. Okay, but that really takes millions of time steps. It's really impractical in like practical real world systems, I feel. Okay, so this memory method is basically a way to overcome that. So if we can remember the experience transition and then like retrieve it the next time we encounter the similar state, we can get sort of the probabilities already. Okay, but I'm saying that actually these probabilities may not even exist, okay, because I don't think the world is that probabilistic, okay, contrary to quantum mechanics. But the real world that we live in is pretty deterministic. Like when I want to pick up my cup, my hand just moves here. You see, I don't exactly think that my hand wouldn't move there. Yeah, I mean, unless there's something wrong with the muscle control.
So Chungmin, I think what you're saying is probably right at these scales. I mean, quantum mechanics generally operates at much smaller scales, right? But you know, I recently saw this article where they said that maybe consciousness or something, or the brain operates on quantum mechanics. So I'm wondering if maybe cause effect may be deterministic at the scales we look at. But what about like when you get like other users involved, like if you're in a multi-agent situation, maybe the actions that people take are probabilistic, right? Because that's a little bit harder to predict.
Correct. To me, I feel like it's only probabilistic if you don't understand the system. So if it's like an unknown system to you, it tends to be a probability. Like but I
mean, if it's people, if you're interacting with other agents who are actually other humans, right? In that situation, maybe you can't really predict what actions they will take.
Yes, correct. So in that case, I mean, if you know the full information of their system, you can actually predict their actions. Like if I already know, like if you play rock the past game, you tend to play paper the next game. I can predict you already.
Yeah,
Then
oh,
it won't be probabilistic. But if I don't know you well, or I don't know the system well, then it appears probabilistic to me. Okay, I mean the other example I like to use is like if you roll a dice, actually it's not probabilistic at all. When you roll a dice, it's like physics, and then like you put down the dice in the cup. Actually, if you know how to do it well, right, you control your sequence of actions, you can always rig the dice. Okay, but because we don't know how to do it well, so it looks like the outcome is probabilistic to us. Yeah. So
yeah, I mean, it's like what so you said, it's a Newtonian approach to the world. Yeah, I mean, Newton and quantum mechanics are kind of at odds with each other, right? So I think that's what you're referring to, right?
Yeah. I mean, to some extent, I actually last time I also have this thought, like in a lot of situations in real world, we don't really have very prominent probabilistic phenomenon. Like for example, the example just now Chong-Ming gives, like when you want to, like when at a traffic junction you turn right, most likely you just turn right. So there's no need to model the probability. The probability that what if you turn left, like we are in a car, it was steering towards the right. I don't know, like I feel like, is it really necessary to model the situation where you turn left or go straight? But I also do agree with your question, where in a multi-agent system, I personally feel sometimes it's hard to have a deterministic approach, because it might need a lot of observation to really get to know what other agents, like what's their behavior pattern and stuff, right? So I don't know on that part how efficient or how effective is the deterministic approach.
Yeah. So okay, so we talk about the multi-agent part, right? If let's say you want to model like a multi-agent system, okay, assuming that the agents keep changing their behavior, even the best RL algorithms will have problems keeping up with it, because it is then going to be like a rock, scissors, paper game. There's no clear winner, right? Like StarCraft, the game StarCraft. Alpha Star, actually, when they play against the professionals, they use 5 programs against them. And the 5 programs are all 5 different programs, 5 different kinds of behaviors. So to the human, always throw the human off guard, because the pro thinks that, oh, the previous program played like that, so I should play like the other way. So like games like StarCraft, there's no clear way to win, because like there's so many different variations. One variation might be better than the other, and so on. So for that kind of systems, I think even the best RL systems will have no chance of winning. Okay, because like there's always a way to like exploit the system. Okay, so what I'm thinking is, even if you just use this memory system to like even model like external parties, and then keep updating your memory based on what is happening right now, you will get more or less the most optimal way to deal with the situation, because you observe what the player does now, and then you sort of like know how to counter it based on like the most recent behavior. And here, of course, the assumption is that the player's behavior doesn't change too much in the short term. So yeah, I mean, if you are playing games like poker, and then the pro poker player keeps changing the strategy, then you are not exactly going to predict the strategy very well. So this method will fail. Okay, but most contexts that we like to use this RL thing in will not be like games like poker, where probability is like inherent like that. Most of them will already be in like situations whereby it's quite deterministic. So I think it's not too big of a problem. Yeah, I mean, I may be wrong, but I actually feel like if we just keep a memory bank with the most like recent transitions, it's actually the best way to make our predictions. Yeah, I mean, you think about it. If you were to play like maybe the stock market, would you want to base your predictions on like trends 20 years ago or trends like just a few days ago? Yeah, so most people would.
But then making this choice is sort of imposing an assumption on the data. It's like this storing the sequence of state actions is optimal if this state action sequence will repeat in this world.
Yes, correct. So we don't know whether the state action will repeat. That's why remember last week we were saying that you should only like store values of reinforce the values of the state if you have seen it again. Like you've seen this state more than one time, you reinforce it. Then slowly you will forget the other states if you haven't seen them. So there's a way of this memory mechanism that makes your memory relevant to the current situation. Because if you don't see the states, it means that they are probably not as important. Yeah, so I think it is still okay. Just using this memory mechanism to like model the dynamics of the world.
So isn't this really just you are making some assumption about Markovianness, right? But
no, there's no Markovian.
But it is true. The next state only depends on the previous state here. But
yes. In that sense, yes.
But instead of having a distribution over states, your distribution is an impulse, right? It's like saying when I'm in state 1, then the next state is going to be it's deterministic. It's not probabilistic, but you can actually think of it as your distribution is impulse over the set of next states. It's actually just one of the next states, as opposed to having a model that includes all the states. Maybe that's a way to sort of reconcile the two ways of looking at the world.
But
Okay,
then that's not Markovian because like if you, for example, if you go to one state and then in like one sequence of decisions, this state is dependent on the previous state. But in another sequence of decisions, this state is dependent on like another state. So it's like you can have one state but multiple actions in multiple episodes, and in that case, it's not necessarily Markovian, or it can be Markovian with a big memory.
Yeah, with bigger memory. Correct, exactly. Yeah, it's a bigger memory. You're right.
Yeah, I guess the Markovian assumption is that the next state depends only on the key, which is an implicit assumption in this table. Yes, but of course, if you want to do how do I put it? Like if the next state is not dependent only on this state itself, okay, then of course we need to model more things inside this state. So one of the key things that this table would work is that if you can predict your next state solely based on your current state. So that's one of the key things for this memory system to work. So I guess if you cannot do this, then it will be very difficult to make your decision anyway, because you won't know exactly what your next move would be. I mean, what your next state be, and then like you can't really predict it. Okay, but over here, the main thing that we need to predict, okay, it's not so much the next state actually, it's actually more like the action, but we store both of them together. Okay, later you will see why this is used, because in the memory retrieval method, we actually need to retrieve the next state in order to do some planning. Yeah, but I think whatever your said is right, like there's still some implicit Markovian assumption here. Yeah, okay, Prof, you want to say something?
Yeah, I would say in this table, if my key is 1, what's the next state? Is it 2 or 3?
It depends on the action. So if let's say if it's a probabilistic action, like you take action A, then it can be either 2 or 3. So one good thing about this memory table is that if the transition is indeed probabilistic, you can actually do a lookup and then you can count the number of possible outcomes as the probability.
So how do you update this table? If I see something, I just append to it?
Correct. So if I, let's say, see a new state like 1, and then the next state is 4 with the same action, I just add in this new state in the table.
Okay, but then
so is probabilistic, we can allow for repeated keys.
Okay.
But if we already know that the environment is deterministic, which is a huge bonus, if I see this 1, 4, what I can do is I can straight away delete away all the tables that contain like 1 and A and not going to 4, because this means that the environment has changed and all these are not relevant anymore. So
is there some form of forgetting? Is there any forgetting in your update?
Correct. So in the method that I did the experimental evaluation on, I assume a deterministic setting and I just erase away all the keys that are irrelevant.
Okay.
Yeah, so this is the more efficient way to learn. But of course, if we grant that there's some probabilistic elements involved because we don't know the full situation, then we can allow for repeated keys. I haven't tested this yet, but if you do some form of like attentional based retrieval, you might still be able to like do your decision. Yeah, so it'll be a bit more inefficient because, as you know, things that involve probabilities tend to be more inefficient. Like you need to count your samples to get the probabilities accurately. So I myself not in favor of probabilistic environments, but I mean, as far as possible, you should try to make the environment deterministic. Yeah. Okay. Anyway, thanks for the discussion. Yes, Evan asked a question. Is this RL paradigm to speed up the algorithm? Yes. We want to make reinforcement learning agents learn fast and adaptable to a continuously changing environment. That's the key aim of this. Okay,
I wonder what would happen if, for example, to retrieve a reward, you need to go through the same state twice.
Sorry, can you repeat that again?
Like, I wonder, so for example, to retrieve this reward, you need to go through the same state twice. And then take, like in the first time when you go through this state, you need to take one action. And then the second time when you go through this state, you need to take an alternative action to get to this reward. In this case, in the table, you would encode this the key as the state, and then action as two action options, and the next subsequent states that it leads to. But then, can the agent figure out that I need to go through the same state twice?
Okay,
to arrive at this particular.
I got your idea. You're saying that this table only allows for one action, right? Okay, so this is the key thing, okay? There's no reward modeling in this table at all. So in the case where you need to go through the same state twice, maybe I just give you an illustration, okay? Let's say I have 3 rooms, right? Okay, then the aim is to get like a key from this room and then open a door in this room. Okay, so you start off with this state in the center, right? Then you can go to the left or the right. So when we start at this state 1, we need to go here to get the key, right? Then we need to go here again to the empty room. Then we need from this state go over to the door. Am I right? So in this case, it might appear that this state here has 2 different actions, right? One action is to the left and one action is to the right, correct?
Yeah.
Yeah, so this is how I reconcile it. Okay, so actually I'm jumping a few slides ahead. I'm saying that this reward modeling is not implicit at all. Okay, what we do is we do goal-directed modeling. So when we are at this state, okay, what I want to do is I want to open the door, right? But in order to open the door, I need to do some sub-goal planning. So the thing is you want to open door. But in order to open door, you need key. So you need to find key. So then, okay, this hasn't been created by me yet, but I think this is a very important point of future reinforcement learning. It's called hierarchical reinforcement learning. So we need to break down based on our goal, which is like open door, we need to break down into sub-goals. So then for this sub-goal, find key, the action that I need to take for this find key will then be to go to the left. And then after I find the key, I go to the open door, and then the direction I need to take is to the right. Okay, so this thing of like where to go next, right? Will actually in this table here, it actually already modeled there. So it's like if we were to say that this action A and this action B, right? And then like this is state 1 and this is state 2 and state 3. The table would already like model it like that. So let me just show you. The table would model like that. If you take action A, you go to state 2. If you take action B, you go to state 3. Okay, but exactly when to take like action A and B, that will depend on basically the goal that drives you. So if I want to get the key, I take action A. If I want to get the door, I take action B. Yeah, so
okay,
in this,
so this goal is so in the current table, it still does not distinguish like different goals, but that's like the next step you are like, so
correct.
You want to add the goal to the key encoding as well. But
Yes,
for example,
yes.
does this table, then you cannot distinguish like that you need to go to fetch the key first and then go to the door, because like the action when you're at state 1, it is like equal probability, and there is like no preference across the two. Like you cannot distinguish between the two actions.
Okay, if you cannot distinguish between the 2 actions, then it will be some form of probabilistic modeling already, right? Because the same action A can go to state 2 or state 3, right?
Yeah.
Then we have to use this repeated keys method. Yeah.
Yeah, and then it's like even with probabilistic method, it's not optimal because in fact, like in this case, you just have like one sequence, like you need to take action A and then B.
All right. No, but if you use like the goal-directed way, you will still take action A all the time because like A is probabilistic, right? But you already know that, okay, if I want to go and get a key, maybe I take action A 50% of the time I reach the key. If I go to the door, I take action A 50% of the time I reach the door. So regardless of which goal you choose, you will still take action A. So you can still solve the environment, even if you don't know like what's the end outcome of your action.
But you need the goal somewhere to inform the agent.
No, as in, even if the transitions are probabilistic, like this is A also, like in the diagram here. Okay, even if the transitions are probabilistic, what will happen is that you will keep trying this transition until you make it. Yeah, so actually this is a very artificial situation. I actually don't really wish to touch more on this because I don't think this is how we should model the agent actually. Yeah, I mean the environment.
Yeah, it's more like a corner case.
Correct. I would like to like focus on the case whereby you can actually have like deterministic transitions. Yeah. Of course, the probabilistic part will need some thinking, okay, which can be done in the future. Yeah, but right now, I would like to just focus on like deterministic transitions with like a goal state as the guide as to where to go. Okay, but thanks for your points. I think those are interesting cases to consider in the future.
Sorry, can I check my understanding here? So it appears to me like it kind of resembles how the classical planning is doing stuff, right? So it feels like you are having this table, then you're doing kind of like, if you start from your goal state, they are doing a backward search based on the table, how you're going to reach this state. Yeah.
No, it's different. This table is just doing the world modeling. It's not even the goal directed part yet. It's just doing world modeling. Instead of doing a neural network, like to do the world modeling, I'm just using a table to do it. Yeah, of course, I think if you were to use a neural network, it'll be fine as well. Just that when you update your memories, sometimes you might update it. So like the problem with neural networks, as what I was saying last week, is that if you like, remember you store like this key value pair as like the input output, and then like if you learn this, maybe this new key value pair, sometimes you might change the weights, then this value might be corrupted because like it's like the output of your neural network, it might be affected when you learn new key value pairs. So I'm not too keen in using like a neural network to do the memory modeling. I tend to use like a table.
So how do you know, like, how do you know your goal state here?
Oh, okay. So here we assume the goal is given.
Yes, I mean, how do you connect that to the table here?
Oh, next slide.
Okay.
Yeah, we haven't reached there yet.
All right.
Yeah. So the reason why I didn't put in the reward inside this table is like this. Okay, if you put in the reward for like this state to this action with a reward here, what this means is that the task must always be the same for this memory. So for example, if the task is to collect the key, then maybe the reward here is 1. Okay, but if the task is getting to the door, then the reward here is 0. So can you see that if you were to store the reward in this table, you will have like infinitely many rewards that you can get because you have like infinitely many tasks you can do. So I'm saying that we don't even put the reward here because it's inefficient. What this memory table is just trying to do is to just model the world, do the world modeling. We leave the reward mechanism out. And in fact, I replaced the reward mechanism totally by a goal-directed system. Okay, so, all right, let's move on to the goal-directed system. Okay, so before we move to the goal-directed system, this is just an exercise, okay? So let's say if we want to like, let's say I ask you to choose. Okay, if let's say you are your hotel or office lobby, and then like you have 1 or 2 doors to choose from in order to reach like your office, and you already like know the way before. Like how would you know like which door will go to your office? Like will you take the left door or right door? I mean, this is a hypothetical question. So I just want you all to like think about it. Do you actually calculate like which door give you a higher reward? Or do you like look through your memory and see like which door you open up? Then you visualize the process of going to your room. Okay, so maybe we just do a poll. How many of you think that we actually choose the right door using a value function in our heads? Okay, no one. All right. How many of you all think that we choose the like right action to do based on like some form of memory? Okay, so it's a yep. Su Cheng. Yeah, okay. So I would say that most people think that is memory. Okay, Evan says value function. Okay, so that's quite interesting because I myself, I cannot think of like how we can associate a value for each action that we do. Okay, so this value approximation is very artificial. It's just used in RL. And actually, to be honest, when I like do certain decisions, like when I walk from from NUS, the like science canteen, and walk to like the engineering canteen, I actually visualize in my head how I would walk there based on how I walked before. Okay, if I haven't walked before, I have to use a GPS and roughly tell me the direction. So that's like the goal-directed mechanism I'm talking about. But if you already have the memory, you can just use your memory and do it. Okay, so that's exactly what we are trying to model here. I'm trying to model how humans think into the AI system. So
But actually, hang on, Chongmin.
Yeah.
Chongmin, I feel like I see your point about memory, but I think what the memory allows you to do is to compute a value function. And in fact, that's kind of what you're doing, right? Instead of modeling it as probabilistic, you're getting the insight from that table. Because, for example, you talk about going to some canteen. Well, you will look at the weather and you will kind of think, oh, okay, I can walk this way. I could take the bus. I could do this.
Yep.
And eventually you'll choose one. But isn't that value function? Like, I don't want to get wet or.
No, but I'm talking about like finding the way here. So like you want to choose like whether you want to get wet or not. That's not exact. Okay, so I'm just talking about like how we can navigate there actually. Yeah. So okay, if you want to say like I want to not prefer the outdoors, right? Because I don't want to get wet.
Yeah.
Then you need to think of an alternative way to get there.
Yeah.
So essentially, you still need to think of like what are the ways you can get there, right?
Yeah. No, I mean, I take your point that we don't just compute arbitrary value functions. And I think memory has a really big role. But I'm just concerned that it's not just memory, it's maybe memory used to compute some objective, perhaps.
All right. So the objective, yes, the goal-directed mechanism, but it may not be a value function.
Yeah, correct. Yeah.
Okay, yeah. So let's move on. Okay, so this just my thoughts on why memory should be used for reinforcement learning. Okay, so supervised learning has worked very well. Like you see the recent advancements like stable diffusion is more or less a supervised learning approach to generate images based on text. ChatGPT-3, I mean, is a GPT system using supervised learning as well to actually match the inputs to outputs. So like supervised learning has a lot of use. And in fact, most of the successful applications so far are supervised learning. And why is that the case? So I've been trying to think of this and I came out with a reason. It's because the target is always unchanging. Like your training set is always unchanging. So it's very easy for your neural network to actually learn towards the training set. Okay, of course, it can lead to overfitting. That's other problems for later. But okay, in reinforcement learning, the problem is, okay, you always have like some form of policy, pi. Okay, you choose an action based on the policy. Okay, and then after that, you choose the action, then you sample the state transitions, right? State, action, state, action, state, action. So like the state, action, reward, and so on. Yeah, so you can sample your sequence based on like your policy. That's on policy learning. Okay, then after that, you can learn based on like this reward here, and then you can update like your policy. Of course, in the value method, you can also put like the value of a state. Okay, you can also learn the value function. So you learn both the policy and the value function. Okay, and that's a very big problem with all these methods because like if you were to do it like that, okay, you can see that it suffers from some form of like dynamic changing targets approach. Like if you keep changing your value here, then okay, what it means is that this policy will need to keep catching up with this value. And this value will need to keep catching up with this policy and so on. So it's like they always call this the policy iteration approach, which is supposedly good in reinforcement learning, but actually this leads to a problem of like chasing each other's tail. Yeah, sometimes you may not even converge that well. Okay, and one of the big drawbacks is also if you learn the like policy or the value incorrectly at first, it might take you forever before you actually learn the right ones. Like I experimented with AlphaZero. If AlphaZero learns the wrong policy at first, it can take you. In fact, it may even be impossible to learn the right one because like it's just that hard to get out of the cycle. So because of this ever-changing targets, and especially this episode rollouts here, heavily depend on the behavior of your policy, okay? Because your policy generates your actions. Okay, and of course, this value will be used to train your policy. So actually, all these are very like, how do I put it? It's very erratic. That's why there's this new field called offline RL that tries to take like huge data sets in order to learn more steadily. Okay, then there's also like other things that are more successful, like fixed target reinforcement learning, like double DQN, you use one network, it's fixed for the actions, one network for the values. Actor critic methods, I saw like at least 5 papers in Neurips that fix the actor while training critic and train the critic while fixing actor. And each of them say that the method is novel. So I think this is something that is, you can see the trend in RL going towards that. And that's because reinforcement learning is very unstable because of this problem of the cycle here. So rather than doing what people are doing here, like fix this, fix that, okay, this actually can still be quite inefficient because, you know, when you have 2 different targets, you fix one, you train the other one, and then you train, okay. Although it's a bit more stable, it still can be quite, it still can be hard to converge, especially if you train the wrong direction at first. Okay, so what we can do is we can use memory as the way to be the target for the neural network. Okay, because this memory is always going to be like roughly unchanging if the environment doesn't change. And this can provide a stable target for the reinforcement learning system to train towards. And if the environment changes, your memory will be updated to the latest change, and then it will be much more easier for the reinforcement learning algorithm to go towards the new change, because the memory, after the change in the environment, the memory will still be relatively unchanging after that. Okay, it's only changing when the environment changes. Okay, so this means that using memory actually is a very it's a much more efficient approach to learn RL than like trying to do offline RL, which takes very long time to train, or like doing this kind of, like, I call it stopgap measures to try to fix RL, which is like trying to freeze one set of weights and training the other. I mean, sure, it can work, but I don't think it solves the fundamental issue of reinforcement learning, which is that basically the way the neural networks are trained are heavily dependent on like the experiences that you get. Okay. So, okay, I might receive a lot of criticism for what I say in this slide, but I think I still stand by whatever I just described. Okay. So how do we solve this then? Okay, so just now you all saw the way to learn the world model using the memory system. So there's also a second branch towards this memory mechanism, which is called the goal-directed exploration. Something like what Prof said about, you know, trying to find like a directed way, like take the bus or take the non-sheltered way, that kind of thing. So you actually have a goal, okay, and then maybe you have some conditions like you don't want to get wet. Yeah, so basically this goal-directed exploration is basically used in order to like find the right action to use, okay? Find the right action to do based on the goal you have. Okay, so this is actually quite important, okay, because, okay, we don't want the memory to store things that are not useful to us, okay, because there's so many things in this world. Okay, imagine you experience every single thing in this world. Okay, you'll be filled with a lot of irrelevant experiences because you only want to do like that many things in your life. You don't want to do everything. So in order to ensure that your memory stores only the relevant transitions for your task at hand, okay, we cannot explore everything. So of course, this statement means not optimal. All right, so I will admit this, because in order to be optimal, you necessarily need to explore everything so that you can get the optimal like set of transitions. Okay, but this will mean that you take millions of time steps to train. So of course, we want to make sure that we only store things that are like most relevant to our tasks. So this goal-directed mechanism does that. So one example of goal-directed exploration is like that. Imagine you want to see this tower in the middle of a forest. Okay, and then you are somewhere like over here. Okay, you don't know how to reach the tower, but what do you have? You know that this tower is over here. So I can sort of like head roughly in this general direction of the tower. Of course, in the middle, I might like shift here a bit and so on. But eventually I will reach the tower. Okay, and this goal, okay, this goal-directed exploration may not give you the right actions actually, but it will serve as like a compass into guiding you there. So like one way of doing like goal exploration is like you just find the Manhattan distance from the start state to the end state like that, and then you like bias yourself towards this. Okay, so this is like, we require some form of heuristic. Okay, and of course, if you want to do like goal-directed exploration, you need to find like sub-goals as well. So this can be a difficult problem to do. Okay, but then this is quite natural for like human decision making, because like when we do decision making, we typically are goal-driven like creatures. Like you want to eat food, you find food. If you want to like go to somewhere, you go somewhere. Rarely will you find a human. Okay. Okay, so this is a very typical use case. So there's this thing called curiosity-driven rewards, right? So whenever you like encounter a new state, you give the agent like some rewards to encourage exploration. Yeah, so imagine you have this goal, exploration driven rewards, where every novel state you get a reward. So imagine what will happen if we do that to a human being and you give him a combination log from 000 to 999. So like, oh, 000 is a new state, then oh, 001 is a new state, oh, 002 is a new state. Okay, do y'all imagine a human being spending hours at a combination log trying all combinations from 000 to 999? Okay, just because every single combination is novel. Okay, can you imagine that? Okay, so actually I would like to just answer that. Okay, so I cannot. So this is actually a very inefficient way of exploration because there's no real like goal here. Maybe the goal is to open the lock, but definitely you won't feel like it's very novel or curious for every single time you turn the lock. But the AI agents that we've given with curiosity-based rewards, they do just that. They are very excited every time they turn the lock. So I don't think that's the right approach to model it actually. But we need to model some form of goal-directedness so that the agent can try to reach the goal. Okay, so of course, this heuristic, I tried with this before. Yeah, I submitted a paper to ICRR for this. Okay, but then I think it's going to be rejected. They said that this heuristic method requires too much handcrafting because you need to, like, for the environment itself, you need to know, like, oh, you need to use like Manhattan distance and so on. Okay, so I've improved on this. Okay, now there's no need for heuristic anymore. Okay, so how do we do the goal directed without heuristic? So that's the next slide. Okay, so this is a key thing now. So we have two networks that we want to encode in our RL agent. So I call this the fast and slow network, paying tribute to Daniel Kahneman, thinking fast and slow. Okay, so my fast and slow is slightly different from what most people would think a fast and slow is, because most people think the slow is just a stack up of the fast. Like Yann LeCun, his JAPA architecture, when he does the hierarchical planning, the slow is just a stack up of multiple layers of the fast system. Okay, but here I'm proposing something different. So for my fast system, it's like this. This is a goal-directed reward system. So you give a state, okay, and then you give a goal state as well. And then the neural network will predict the action. Okay, so that's as simple as that. So there's no heuristic needed. So given a state and given the goal, predict the best action that you should do, the first action that you need to do in order to step towards that goal. As simple as that. No heuristic needed. You can learn from experience. Okay, so that should put the ICRR reviewers at ease, knowing that their criticism has led to something interesting happening. Okay, so next we have the slow system. Okay, the slow system is basically a memory retrieval network, like the table that you saw earlier, the key value table, that will basically match the current state. Okay, there's a state here, which is the key, and the value is the next state, S prime, and the action to get that state. So we can do this memory retrieval system, okay, to look ahead multiple time steps in order to get the outcome. Okay, so this, I will describe this mechanism in the next slide. Okay, so what we can do then, okay, every single time step, we can use hippocampal replay. Again, we lead back to the idea of hippocampal replay. We can use hippocampal replay to update this transition, okay, to this fast neural network. Okay, how? Okay, by actually doing a goal-directed learning. Okay, so this hippocampal replay with the goal-directed learning, I will do it on another slide as well. So yeah, maybe I describe the whole idea first, then you'll ask questions. I'll give some time because I want to go through this idea, okay, as a whole. All right, so what is this slow system for memory retrieval? Is like this. So I envision this to be something like a mini column in the neocortex. So neocortex has many mini columns that can do parallel processing. I posit that that mini column can help in future state prediction as well. So what we do is we have a state S1, okay, and then we like reference the memory. So there are different branches. Okay, I like to call these branches like minions because they are like different workers helping you to do the work. So we basically reference the memory. Okay, we check whether there's like a memory with the state 1 in there. Okay, and if we have that memory with the state 1 in there, we can actually return, like randomly pick one of the next state, like maybe state 2, randomly pick the next state. And then after that, we can reference the memory again for state 2. And then we can come back here. Maybe you can get like state 3 and so on. So if let's say state 3 is your end goal, what we'll do is we'll come down here, and then this worker here has found the goal in 2 steps, because like state 1 to state 2, state 2 to state 3. Then we can have another worker over here. It queries state 1 again as the input, queries the memory, and the memory returns state 3 directly. Okay, and then we can say that this worker has found it in 1 step. And then we have another worker which takes state 1 here, finds a memory over here and comes back. Maybe it finds like state 5, state 7, state 9, but in the end, after like maybe 10 time steps, so over here is like 10 time steps maybe, it finds nothing. So over here is nil, like it doesn't have anything to offer. And over here is nil also. So you can treat this like multiple look ahead trees, whereby you try to search in your memory whether you can find like a sequence of steps to lead you to your goal state. Like earlier on, I talked about the 2 doors, the left and the right door. It's like trying to trigger your memory to find like a sequence of like steps that you can take in order to reach your office. So if you can find a sequence of steps, very good. So what we can do next is we can then find out, okay, oh, this is 1, this is 2. Okay, so what I can do is I can then focus on this thing here and say that, oh, I will pick the more efficient option. I will go with this 1 step. So from state 1 to state 3, directly like that. So see which branch has the shortest trajectory and use the first action from that trajectory. So the action that I took to get to state 3, this action A will be the action that I execute. So this memory retrieval mechanism is quite versatile because it like does like random sampling of the next state. The reason why I choose to do random sampling is because if there's a lot of states, it can be very difficult to do brute force, which means like you expand out everything. So doing random sampling is more efficient. Of course, it also means that you may not find the memory all the time. Yeah, but this generally works quite well already, even in the environment that I tested in. Okay, so maybe I pause here for a while because this is quite important. Anyone got questions with this architecture of how to do the slow retrieval?
Why is it called a network?
Say again.
Why is it called a network? Because it's like, to me, it looks like there are multiple independent agents trying to retrieve the next state given memory, and then you find like the agent that does like the best thing.
Yeah, so it's not a neural network. Yeah, right.
Okay.
Yeah, I guess you can call it the memory retrieval mechanism without the network. Yeah, and I guess the network I was thinking of is like a network of agents.
I see.
Yeah.
And this overrides the fast mechanism, right?
Yes, this overrides the fast mechanism.
Okay.
Yeah, so I haven't got to that yet, but let's move on.
Right.
So okay, so now I talk about continual learning. Like, okay, so I already said earlier like why I think the world is deterministic. Okay, I'm gonna get some criticism for that, but I generally think this is the case. Okay, so even if we don't have deterministic, we can just add the transition to the memory and do some like count-based probabilities. Okay, but if deterministic, we can remove all existing memory which does not match the experience, which is great because your memory will always be the most updated. Okay, so most updated transition. And then I haven't implemented this yet, but you can also add in some form of strength for the memory so that you will remember transitions you see more often for a longer time. So this means that like this particular memory might be more important. Yeah, like, you know, like when you memorize lists of words, if you memorize multiple times, you will recall it better. Like there used to be people that used to memorize the entire Bible. They also do it like that. They keep repeating verses and verses until they can memorize it. Then they move on to another verse. Yeah, so this system can be useful for like continual learning as well, because if the states keep repeating, it probably means it's important in the agent's life. Okay, so let's move on to the fast learning mechanism. All right, so this is how this overall system works. Okay, so I actually like this idea so much that I implemented the code for this like over the last week. Yeah, so I'm very proud to announce that actually it's working. But let me just describe how this works. So first, we do like a state and action prediction first. So we have a goal state in mind, and the agent knows its current state. Of course, this means that you have a goal state. You can quantify the goal state, which may be a problem in current RL because we may not know how to quantify the goal state yet. But in the discussion, I can talk about like how we can do this in the future. So this is actually more like a 10-year plan. It's not so much immediate, but I think this mechanism is correct in the right direction. Yeah, we just need to work on it more. Okay, so next, the agent queries the fast neural network to get some action probabilities for the goal. So over here, of course, this only works for discrete cases here because like it's a softmax across all actions. Okay, I'm still thinking how to do it for the continuous case. So if you have any ideas, you can let me know. Okay, but this is how we do explore, exploit, all right? So we have action probabilities ranging from 0 to 1. They basically sum up to 1 for all the actions, like action 1, action 2, action 3, and so on. So all these are like the probabilities of like what the network will predict. Okay, so like, for example, if I have a grid like this, okay, my initial state is like maybe 0, 0. And then I want to go to 0, 1. Okay, so up, down, left, right, right? So let's say I have the probabilities for this up, down, left, and right. So maybe what I'll do is I'll predict like the probability of you going up is maybe 0.01. The probability of you going down is 0.01. The probability of you going left is also 0.01. And the probability of you going right should be 0.97. Okay, so this is trained like using supervised learning. Okay, how it's trained, I'll show you in the next slide. So basically this goal-directed mechanism, okay, will give you the action probabilities. So given like a starting state 0, 0, and then you want to head to the state 1, 0. Actually, it's 1, 0 because it's x-axis. You want to head to the state 1, 0. Yeah, so let's just talk about this 0, 0 to 1, 0. So this is your start state, your current state, and this is your goal state. In order to head there, the action that you probably need to take is this right action. So this will be the action probabilities. And then here we have this visit count here. I take a square root in order to like do an exponential decay. Okay, so these visits will basically tell you like how much of the states you have visited so far. So let's say if I have done like up, down, and right, maybe my visit count is 1, 1, 1, 0. So basically, the more times you visit, the less you want to choose the action. So basically, we take these two things and you sum this up. So let's say we have 0.01, 0.01, 0.01, 0.97. We will get this. So we'll get like minus 0.99, minus 0.99, minus 0.99, and then like 0.97. So what we'll do is we'll pick the up max of this. We'll pick this action here, which is right. So as you can see, after we pick the action right, then this one will be updated to 1 again. Okay, and then this value here will then be updated again based on this. This one will become minus 0.03 the next time we see this. Yeah, so this is one of the ways to like, if you explore that state more, you choose it less. Okay, this is, sorry, if you choose that state more, next time around you try to explore other states. So this is one way to like encourage the agent to explore new options when one option has failed. So this explore, exploit, I find that it's actually very important. In my previous work in the Neurips workshop, without the explore, exploit, you can't solve the environment at all. So this is very fundamental to a reinforcement learning agent. Okay, so this action will then be like the preferred action to choose. So you can treat your system one like a compass. If I'm lost in the woods, where should I go to find the tower? So this is the compass. So system one is the compass. Okay, but if you already have in your memory a way to reach the tower, should you use your rough idea of the compass or should you use the one in your memory? Okay, you should use the one in your memory, right? Because you already have a path, a list of steps in order to reach the goal. Then you should use your memory. You should use this system too. If you have a list of states, and then it's already like the most optimal states because system 2 actually chooses the shortest trajectory based on the mechanism I talked about earlier. So this enables us to do this slow memory retrieval. Okay. And if we can actually have it, we override system 1. So this 2 will give us the action. Okay. And basically what we do next is that we update the memory retrieval network with this new transition because we have the action, we have the state, we have the action that we can run through the environment to get the new state. So we can actually store this transition here into the new network. And then we can also remove all memories that conflict with the current transition. So for example, if we have like a state action, and then we have like a S prime prime, which is a state that is different from what is predicted, we can then remove all of this kind of transitions from the memory if it's deterministic. Okay, if it's probabilistic, we can keep it there. All right. So yeah. Now the secret sauce for this method, okay, this is how we train the goal-directed mechanism without any heuristic. Okay, I repeat, without any heuristic. Okay, so this is heavily inspired from the mice diagram that you see here. So I've been looking at this mice diagram for close to like a year, I think. Every time I look at it, I think of something new. So this, whoever created this, Frank and Ju, I actually thank the two authors who created this, because actually is the source of a lot of inspiration for me. So let's see how we can do this fast network training. Okay, so what we will do is we do this experience states training first. So given at every single step of time, so this hippocampal replay is not just done at the end of the reinforcement learning episode, just like most reinforcement learning algorithms. We don't do it at the end of the episode. We do it in between the episodes itself. Every single step that you make in the episode, you can learn already. So you can actually learn while being like trained on the environment. There's no training and testing phase for this. Everything is a testing phase already. Okay, it's an online learning mechanism. So what we do is we start from like this is your current state. This is the current state now. So in order to do like a state and the goal, so this will be the state and this will be the goal. And then we have an action here. Action, A prime, based on the action histories we have, A prime, and so on. So this actually like tells us like how we can actually like learn already. Like for this goal state here, which is the current state here, we can actually learn this arrow, we can learn this arrow, we can learn this arrow, and we can learn many other arrows for each of the states. And then the same thing we can do for the other side, this part here, this forward replay. If we can actually have the trajectory by the slow neural network, what we can do is we can treat all of the future states as your goals and your current state as your current one, as your state here. And then you can train this arrow here. And all this will train with this action here, the action that you have taken. This arrow, this arrow, this arrow. Yeah, so I will treat like the way you do this is to like retrieve the states. And then when you go down here, you're actually learning this goal-directed mechanism. Same thing for here, you're also learning the goal-directed mechanism. And there's a reason why I designed the goal-directed mechanism like that. Okay, can y'all see that if let's say the current state is shifted one step to the right here, like if the mouse is over here, you can see that the arrows will be like that. 1, 2, 3, 3, and so on. And the arrows on the other side will be like that. 1. Okay, so you can guarantee you learn all possible start and end positions as you transit through the environment. Okay, can y'all see that? Okay, it might be hard to see, but you can treat this mice position as your index buffer. And as you move your index buffer one by one, you learn all possible combinations of start and goal states in your episode itself. Can y'all see that? Who cannot see it? Then I can explain it. Can y'all see that the way this setup is done is so that you can learn all possible start and goal configurations in that particular episode itself? Or maybe even more, because like all this like the future expected states which can change. Yeah, but as you move the mice like that, you learn every single start and goal state, which means it's very efficient. You don't just learn your goal state here. You also learn all the, let me put here, also learn all intermediate goal states and all possible start states from experience states. So it's very versatile, because from like one path that you take, you learn all possible combinations, which is quite useful. Because like, for example, I go from point A to point B in my real life. Let's say I have a point C in the center. Okay, so real life example will be like this. I go from I like to use the science canteen again. I go from the science canteen to maybe the engineering canteen, and in between is the library. So if I travel like that, it also means that if I want to go from the science canteen to the library, I should already know the way because I passed by the library, right? Also, if I want to go from the library to the engineering canteen, I should also know the way because I can start from the library and then imagine myself to the engineering canteen. So this is a very natural construct. So you use one experience and you can use it for many, many tasks. And that's the beauty of this mechanism. You can then do for arbitrary start and goal states, and you can learn a wide spectrum of tasks. So you experience only one episode, but you can imagine that you can use whatever you learn across a lot of different episodes already. Okay, can y'all see that? Okay, who here needs explanation? You can raise your hand now. This one is quite new because I honestly haven't seen this anywhere else. I came out with this recently. Okay, so you raise your hand. Anything you want to ask?
Just this part, like, yeah, the part, can you repeat again?
Okay, which part do you not understand?
So you can make use of, you learn for one task, but you can like use it for any task that require this knowledge.
Oh, yes. Okay, so you see, if let's say this is my start state and this is my goal state, right? If let's say in another situation, I give you the start state over here. Do you already know this arrow here from the previous training? You already know the arrow, right? Because like this is already reflected in like your future state prediction here. So what this means is that you already know how to solve like another task, even though you haven't seen that task before.
How about the cases where just now you gave the example of going from one place to another, right?
Yeah.
So I assume like even you want the route, but the other way it also works, right?
So let's say this is the science canteen, and this is like the library, and this is like the engineering canteen. So if you already found the way from the science canteen to engineering canteen that passes through the library, you also know that you can go from library to engineering canteen, and you also know that you can go from science canteen to library. Okay,
Well,
you're asking whether the other reverse
because
right?
I remember last time you gave an example where it's hard for human to.
So you want to do this reverse example, it doesn't work. Okay, because if you think about it, when you do a reverse drive-through of like a circuit, like of a road, it kind of feels different, right? I mean, the same road, but it actually feels different when you drive it reverse. So I think that just like how when we retrieve memories is only a directional retrieval, you always think of memories as going forward in time, right? You don't think of memories backwards, right? It's not natural. So in order to reverse your path, it's also not natural. You have to learn it separately.
I see. Okay.
Like for alphabet A, B, C, D, E, F, G, you can learn it forwards. But if I ask you to recite the alphabet backwards, can you do it?
No.
Not really, right? So this is the same principle. So we should only focus on directed start and goal states based on our experiences, not the other way around, because sometimes the transitions don't apply backwards.
All right.
Yeah, okay. Anyone else got questions for this? Okay, so this is actually very cool. So if you combine these two ideas together, the fast and slow, you get very, very like powerful mechanisms. So maybe I spent about another 5 to 10 minutes describing the experiments that I did. So this is the validation. So what I did, in order to just show that this actually works, we do a very simple experiment. Starting at like a square 0, 0 to 9, 9 in a 10 by 10 grid. We can move up, down, left, right. No obstacles at all. All squares can be done. All squares can be moved to. We see whether the agent can navigate to the goal state efficiently. So the agent, the caveat is cannot see the entire grid, only knows its current position and the goal position. Okay, so we try a Q-learning approach versus the memory-based approach that we just showcased just now. So this is the results. So Q-learning, I tried like you need about 100 episodes because Q-learning requires some form of random action selection at first to learn. Like the behavioral policy is a random. So like you need to sort of do random action like for about 100 times. Okay, I mean, it's between 50 to 100 because I tried for 50, it didn't work. So 100 works. So about 100 times, then, okay, it achieves successful episode, like the minimum steps, which is 18. Okay, compared to the memory base, within 2 episodes, it learns enough to like solve everything already. So you can see that if you just look at 100 versus 2, it's like 50 times increase in efficiency. Okay, of course, Q-learning, we use random, it's not very efficient. If we use a count base, maybe it will be faster. Okay, I haven't tried. But this is one reason why I don't like to use value-based approach, because earlier I said that the value needs very long to backpropagate. Okay, this is why. Okay, it really takes very long to learn. And current RL systems that are based on value mechanisms are all very inefficient to learn. So we could somehow use some form of memory base and goal-directed base. We can actually improve a lot on the speed of convergence to solving the optimized the minimum to reach the minimum number of steps needed. Okay, so I found that actually this is too easy for my agent because obviously it's very powerful. So I made the experiment harder. So now the start and end state are always changing. A random start and random end states. We have obstacles which block certain squares. So the first 10 episodes, the obstacles are like that. I think it's like that. And then the next 10 episodes, the obstacles are like that. So it's like blocking the middle. Yeah, there's a gap here also. Yeah, so this actually forces the agent to learn like new strategies to solve it. So we test the memory approach with like with some ablations, like without the slow memory, without the fast, and without the fast and slow. And we can see that this is what we get. So the baseline is, okay, so still a little jumpy because I didn't give it enough time to stabilize. But if we let it run enough time, soon it'll reach the minimum already, like or very close to the minimum. Okay, so it's like plus 629 steps from the minimum because of all this like plus 100 here. But you can see that with the goal-directed mechanism, it actually learns very fast. Like it's like almost optimal here already. If I let it run a bit more, it will reach near the optimal as well. Okay, but without the slow memory retrieval, okay, you can see that it's like it like takes very long to converge. It's not very efficient because like sometimes the goal-directed thing like you might point to the tower, but then you might not have the right path to go there because of the obstacles. So the goal-directed method only gives you the broad direction to go. But towards the end, you need to rely on some part of your memory. Okay. So this is also the same thing for like, I don't know, when you're driving. I mean, if you're going to a new place, like the goal-directedness only gives you like so far. And then towards the end, you sort of need to use like some form of like external help to get you there. But the next time you go there, you need to rely on your memory. Oh, I should turn left at the first fire hydrant and so on. Yeah, something like that. So you still need some form of memory to help you. See over here, it's so much more efficient compared to this. Okay, if we do it without the fast memory, without the compass, it's also quite inefficient. You can see that over here you have stuff like that. Okay, but it's also about the same as without the slow. Okay, what is more critical is without both the fast and slow, we're just using the count-based approach. You can see that like this is what happens. We don't solve it most of the time. You can see that the transitions are all the same for all four of them. So this shows that one thing, the count-based approach is not sufficient. Okay, the count-based approach is not sufficient to learn well. You can actually need to use also memory for learning. And the memory mechanism can learn even when the environment changes. And of course, the other thing is like the value systems are very slow to converge. Okay, so this I believe is very true because I asked a lot of posters like, if I change your environment, can it still work? Probably not. Yeah, so this is really one of the key drawbacks of current RL. So yeah, I think now, I mean, it's quite late already. Can I check whether you all want to see the code? If not, I can do the code another day. Yeah, because I think I need about 15 minutes for the code. If not, I'll do the code another time.
I think it's all right.
It's all right, Mince?
Yeah, I mean, good. I can see it now.
Oh, you all can see now? Shusheng, you okay also? Sorry, I just get your, it's a bit too late for you.
I'm fine.
Okay, I'll go run the code now. Not go run, I will just show you how the code works. Okay, so let me just share my screen. Can you all see the code now?
Yeah.
Yeah.
Yes.
Okay, so I won't be running the code because I already ran it before, but I just want to show you what happened. So first, I want to do some form of tests. Okay, basically I want to, okay, maybe I can just run it now. Yeah, I want to basically test whether or not like I can learn the next states and actions by supervised learning. So what I do is I create an environment and then like create a few sample actions, like go right, go up, go left, go down based on the current state and the goal state. Then I also get the next state based on like the action that I've taken. So I create a list of states, I create a list of actions and a list of next states. Okay, so I want to see like how efficient is it like to learn the action and learn the next state. So you can see like over here, 2, 4, 2, 0. Okay, so this means that I should move like, if this is the x-axis and this is the y-axis, and 0 is like at the top and 4 is at the bottom, I should move down. So the move that I should make is like 1. Okay, 1 is like move down. Yeah, so you can see that this start state and the goal state corresponds to one action here. And then after you move, this will be the final state. So like 2, 4 to 2, 0, if I move down, I will get 2, 3. Okay, so now the question is, should we do a next state prediction? Okay, so this is what I try to experiment on. So the neural network is very simple. It just takes in the 4 current and the goal positions, go through 2 dense layers of 1 to 8. Okay, and then after that, outputs like a softmax of 5 different actions, where like there's also a no-go action, like don't do anything action. And then I see whether like it can like learn. Okay, so this is how the model looks like. Input layer, 2 dense, and then output is a softmax. Okay, so what I do is I do Adam and then like do accuracy, and then I split 80% train test split. Okay, the 80% training and 20% test. You can see that on the test set, it performs like 99% after 5 epochs. So yeah. Evan, you asked whether this notebook will be shared, right? Okay, I would like to say that right now, not yet. Okay, because I still intend to go and do more experiments on it. And it will still be also used for the next paper I'm publishing. So not so soon. But if you are interested, I can share with you privately. Yeah.
Can I check? Is that the fast memory part?
Oh, no, this is not the fast memory. This is just an experiment to see how easy is it to. Oh, yeah, this is for the fast memory. Yeah. It's just how easy it is to predict the action based on the current and goal state. And indeed, it's quite easy. You see, like within 5 epochs, I get it up to 99% already.
Did they use the table?
No, this fast memory doesn't need the table.
Then how does it know?
It's just based on the experiences that you have. So like the past trajectories of your states, you can train the start and the end state.
Oh, that's the table, right? That's the count.
I mean, now I just randomly generate the start and end states. Yeah, the table is for the slow method. That one's different.
Okay.
Yeah. So this is the fast method, just current state and the goal state. Okay, so this is just to see whether we can predict the next state or not. Because like a lot of methods like Dreamer V2, they like predict the next state as well. And they show like in Atari games, they can predict exactly what the next state happens. And I'm very skeptical about that because actually the Atari network, the Atari games actually you can solve by memorizing a fixed set of actions. But yeah, let's just see whether like this can work. So the same network, just that instead of just predicting only 1 dense, I predict another 2 more. And this is the X coordinate and the other one is Y coordinates. And let's see whether we can learn it. So we learn it for 30 epochs. And you can see that at the end of it, my accuracy for the action is 1. Okay, but you can see that it took quite long for the accuracy to like reach 99%. I mean, it took about 9 epochs. So it's like if you learn the other 2 as well, you actually compromise on the accuracy of your actions. Okay, and then the next state prediction accuracy is not that great also. It's like 88%, 85%. I got it 90% once, but in order to predict accurately your next state, you will need a lot of experiences because you need to know what the next state will be based on the previous state. You will need a huge data set of collected experiences. And that's probably why offline RL is used, because offline RL can create a huge database of experiences. But that's very inefficient, don't you think so? I mean, you need like so long to even learn the next state. So after I did like this experiment, like over here, like this 4-1, 4-3, you're supposed to predict the next state is 4-2. You see, you predict wrongly. So if I run for another 30 epochs, probably I can predict again. I guess so. Yeah. If I run another 30 epochs, let's just run another 30 epochs and see whether like you can predict accurately. So now it's 98%, 96%. So you can see now it predicts 4-2. So yeah, it takes a while for the next state prediction to be done. And you can imagine if we change the environment, you're gonna need the same or even more number of steps in order to train the network to predict the correct outcome. So that's one reason why in the end I've decided that the fast goal-directed mechanism doesn't predict the next state because it just takes too long to learn. Okay, but of course, if your environment is static, doesn't change, maybe you can consider predicting the next state. Yeah. Because I mean, it does converge after a while. It just takes very long. Yeah. So now we do the experiment with the 0, to the grid size -1 grid 0, to 99 basically. So this is the experiment. I start and go state, and then there's some forbidden squares. We make sure that we don't spawn in the forbidden squares. Okay, for the first experiment, there's no forbidden squares. So this is a breadth first search I did to find out the minimum number of steps needed. Okay, and then these are the, if you step, what will happen to the next state. Okay, if in the forbidden state, we don't move at all. Okay, and then what if we complete the environment, we give a reward of 1. Okay, so that's all. So the Q learning approach uses this method. I update the Q value function like that with the next state prediction, the one-step look-ahead prediction. My alpha is 1, my gamma is 0.99, the discount factor. Okay, over here I did num actions as 4, all right, instead of 5, because we don't want the don't move state. We can just move up, down, left, right. So basically the first 100 episodes I do random action. The next episode I just choose the maximum Q value based on the current state itself. So yeah, we update the Q value using this function that we showed earlier. Just that if it's at the terminal state, then we don't need to do the next state prediction. These are all very standard ways to do Q learning. So yeah, I coded this out like a few hours ago. Yeah, I'm very familiar with coding this. I coded this a lot of times. so basically this is how the Q learning looks like, and it gives you like this graph like that. So like if you see it train like 100 episodes, then it can converge. Let's try to change this. Okay, let's say I change my episodes to 100. You can see that it doesn't even learn at all. Okay, so I don't know, 150. I don't know how many will it take to learn. I guess I only train on 100 and 200. Okay, 150 looks like it learns also. Yeah, so there's like some sweet spot that it doesn't learn. So I mean, we can configure and find out. But definitely it's above, so 120 doesn't learn, somewhere between 120 to 150. So you can see that the updating by the values is actually quite inefficient. So then we do the memory-based approach, which is basically the same thing that I showed you all earlier. Okay. Over here, I got some explanation that I need to do. So like what I do is I have some like parameters here. Okay, but the first thing you need to know is like these are the number of episodes that I do, like 10 episodes. I start with like the environment here, start state and goal state defined, forbidden square is nothing. I store like state history, action history, and the episode memory. So what I do next is that for each of this step, okay, we use the fast neural network to get the general cue for direction, which means that we get the action probabilities of the current and goal state. After that, we do explore exploit to choose the action, which is basically based on the episode memory, which is basically the memory that you only experience for that particular episode itself, not the total memory. For this episode memory, what we do is we just add the action counts by 1 for each experience action. So over here, each 2 is basically the action itself. So with this, we can then do our explore exploit equation like that. The action probabilities minus away the exploration constant times the square root of the action counts. And then we take the argmax. So this gives you the explore exploit trade-off for your action. So next we do the forward replay. So this is basically this is the slow memory retrieval method. So we have our minions, okay, it's in a priority queue. We do for like parallel threads here, I do 100 parallel threads. I start with current state as my state. I search in memory whether there's a match or not in this state. If there's a match, I pan it to matches. And then if there are more than one match, I can just randomly choose one of them as my next state. Okay, and then I keep repeating this again. I just check whether it's the goal state. If it's not, then I repeat. Like this is just a random rollout. So eventually, if we have, so I do it for maximum 10 look ahead steps. If there's a match, okay, I just pop from this priority queue, which will be, because I store the priority queue based on the index of depth, which is the number of look ahead steps. So this will be the action with the minimum number of look ahead steps. Okay, and if we can find an action like that, all right, we will store the action and we'll override this action with the slow memory retrieval, because the slow memory retrieval is the most accurate one compared to this generic goal-directed mechanism. Okay, after that, we will then do like what I did for the fast memory. We will learn like given the current state all the way to all the possible goal states along this state history. We will learn the start state and action, and we fit the model, the goal-directed method. Okay, next we perform the action. Then we update our memory and the episode memory. And then now we delete the irrelevant states where it doesn't match the environment transition. Okay, this is important, by the way. If you don't do this, you might get an inaccurate memory retrieval next time if the environment changes. Okay, we keep the memory to a fixed size. Okay, append a state history, append action history. Okay, once we completed, we just print out our best and actual steps. And if we haven't completed, I also print this out. And the last step is basically the backward replay, basically the existing states replay. And this one is basically using the current state as the goal state. Okay, which is the current state you are at as the goal state, and all the previous state histories as your start state. And the action history will be your action. Yeah, so we train the model like that. These details are the same as the slides. Yeah, so you can see that it learns very fast. Like after even the second set, it already found the actions already. So you can see that if we use like the goal-directed mechanism, we can get like a very nice list of states that actually correspond to like reaching our goal. You can see that it solves very fast. Yeah, then we also do some experiment with like the random start and end points with like some forbidden squares, like what I described earlier. So after 10 episodes, it will change, and then you can see that, oh, maybe I shouldn't run this. This takes a bit of time. But yeah, so the rest of the results are as shown in the, I mean, there's little change in the code. The only change is up here. So you can see that actually, like, it takes a while to learn, but it actually, this is considered quite fast already, because like you can see that this runs the entire episode like in almost 1 to 2 seconds towards the end of the training. You can see that the start and end states are all random. Yeah, so actually it's quite cool. I mean, we can skip the running of this because it will look like this. Okay, and without the memory and so on, I just remove the slow look ahead. Without the fast goal-directed approach, I just basically set this to 0, the action props to 0, so that there's no bias in the goal-directed mechanism. And then without both, I just set this to 0, and I remove the slow retrieval, and it performs the worst. Okay, any questions on this?
Sorry, I'm still quite confused on, so if the slow memory is the better one, so why would you want, like, sometimes you still want the fast memory?
Oh, both are important. Okay, without the slow memory, you can see that it actually does quite poorly, right?
Yeah.
Yeah, so the slow memory is like, because the goal-directed one is just give you a rough direction of where to go. But the slow memory is like your last mile. It will tell you like how exactly to reach your destination. Because you have been through there before, you can just retrieve based on your memory, and you can repeat the same set of actions.
The slow one is the one make use of your whatever.
The slow one is based on the table that you saw, the memory table. You will just randomly sample the next state from the memory table, and then you see whether they hit the goal state.
Okay.
Yeah, so the slow memory is actually quite important, because if you just rely on your fast neural network, you may not actually converge that fast. Because, okay, one bad thing about neural networks that you must know, okay, is that neural networks take quite some time to learn. Okay, they don't converge very fast. Okay, but they are very, what do you call that? They are very fast at giving you a result. Like once you have trained the network, you can boom, and out comes the value. But in order to train the weights, right, it might take quite long to train. Okay, but your system to the memory method, okay, it trains very fast. Okay, because it will be updated straight away with the new samples. So with the memory method, actually, you actually learn very fast. You adapt very well to the environment. So that's why there's a need for both the fast and the slow. Okay, fast retrieves fast, but learns very slowly. The slow one learns very fast, but then retrieves very slowly. So it's like both complement each other actually.
So the slow one, right? So you do random sampling on the past trajectory.
Random sampling based on the memory table. So like with the current state, I sample what's one of the random states from the memory table. Then I sample again until I hit the goal state.
Oh, so you do random sampling until you hit the goal state.
Yes.
I see. So why don't you do a search?
Because I may not know how much to rank my states. If I were to do a state search, I need to give a value for each of my states.
What I mean, you don't really need the value, right?
Yeah, what I'm doing is I'm doing like a random route. Yeah, I didn't do a like breadth first search kind of search, but you can do a search also. I just think that the search method may be infeasible if it's
memory is too large.
Yeah, I mean, of course, if you were to do a search, it's the most efficient, because like you do breadth first search alone will be very powerful already.
No, I'm talking about like the backward search in the classical planning. So because you already know your goal state, right? then you start from there, you do a backward search to see like what's a possible initial state.
Possible. I mean, you can use that to like plan. Yeah, but all this will introduce some form of like extra complexity that I guess it can help to solve it more efficiently if you do it correctly.
Do you have a like a worst case guarantee on the complexity if you use sampling?
Random sampling, is it?
Yeah.
Yeah, I have a worst case guarantee, because the guarantee is that you will never exceed like the amount of computation time needed for X number of steps. If you do X look ahead steps, it's just X look ahead steps. I mean, like this for loop here. This for loop here will always like give the same kind of complexity each time.
But the thing is, you cannot guarantee use random sampling. You can actually find the correct, the right one. That's why sometimes you need the fast memory, right?
Yeah, the fast, actually without the slow memory, you can still solve the environment, just that you will take a bit longer. So having the slow memory is not a necessary condition to solve it.
But I thought the novelty here is the use of the memory, right? That's where you begin with.
Yes, correct. So this is, if you treat this like model-based planning, this is the model-based planning part. But I'm saying that even if you fail to plan, it's still okay.
Oh.
You will just incur some like some more time needed to learn, but you can still solve the environment eventually.
By just using neural network?
By just using the neural network, yes.
Because my concern here is you just do random sampling. Do you actually get the like fragmented segment of the trajectory?
Assuming your memory is accurate, you should, all this can string together into one trajectory that is stable. Okay. Assuming your memory is accurate.
Okay.
And the environment hasn't changed. So if the environment changed, you need to update the memory by doing stuff like this, by removing like irrelevant states and or so on. Yeah, I get your point that like the memory mechanism is mainly used in this, but I would say that the goal-directed mechanism here also uses memory, you see, because you need to like do some form of replay of your previous states. So this is also using some form of memory, just that it's not memory in the form of like a lookup table.
This replay is more like the one used in DQN, is it? Oh,
it's very different. DQN replay is random replay. They just randomly sample a transition and replay it. Yeah, it's very inefficient. I've tried DQN before on CutPoll. Takes about 600 episodes before it converges. Yeah, TPO takes like 1 or 2 episodes. So that's a comparison. Yeah, random sampling is very inefficient for replaying.
Okay.
Yeah. Okay, if not, I shall go back to the slides. Okay, so let's just end off with a very like simple thing. I'm not going to focus too much on this. This is just one last part of the memory framework that I want to share. Is about how to make the agent survive. So like we have 2 pathways, like reward and pain. All right. So of course, like we don't want to explore everything, because like sometimes you can die if you explore the wrong things, like you jump off the building and so on. So if it leads to a death of the agent, is bad, because you only live once in real life. So if you only store like only the good experiences using the reward thing, we may forget what's dangerous and repeat them. Okay, so this is a reward-based method. Okay, but if we were to tie in with the goal-directed method, I say earlier, this reward pathway can also be the goal pathway. So rather than put this as reward, we can put this as goal-directed also. Yeah, I mean, but in the traditional RL case, we can still use reward. No issues. I'm just saying that we might need to add in another pathway called the pain pathway, where you remember all the bad experiences, okay, and strive not to repeat it. Okay, this is like how it's processed in like amygdala, the fear response, and the motor systems, the basal ganglia to retreat away. Okay, so this may already be inbuilt biologically. Okay, of course, the reward pathway is similar to the dopamine prediction pathway. Okay, so these 2 pathways basically, one help to do long-term planning, which is the reward pathway. Okay, to find the set of states to visit to get the reward. Of course, this is the slow learning that we talked about earlier. Okay, or you can also do the goal-directed pathway, which is what I was talking about. And the pain pathway is the short-term reflex. It's like constraining your actions, okay, to prevent the agent from immediate harm. So what this necessarily means is that if you do a reward and a pain pathway, your agent might be inefficient, because the pain pathway might constrain some of the available actions that can be optimal. but it does so for the sake of preserving the agent's life. Okay, so both methods can also use, like, you can also learn by a memory retrieval system and a predictor system, like what we did for the goal-directed pathway. So how this is done, I haven't done this yet for the pain yet, but this one all is future work. So whatever I described to you here is like part of a 10-year plan that I have, okay, to use memory for, like, actually not just RL, actually, you also use it for other, like supervised learning. You can also probably use some aspects of this as well. Okay, but I'm focusing only on RL because I'm interested in reinforcement learning. Okay, so if not, that's all for the presentation. Thanks so much. So here are some discussion questions I have. So the first is like, how should we explore the environment? Should we use like a random search, random sampling, like what Q-learning does? Or should we go with like goal-directed, like exploration? And of course, I mean, over here, my answer would be goal-directed. Anyone likes to differ and say that random exploring is better? Okay, if not, I would say that most people would think that goal-directed is better. It's more efficient because it gets you to where you want to do. Okay, the next thing is like, how do we store like action, continuous action and state spaces into memory? Okay, this is tricky because right now the state and action spaces are discrete. Okay, so yeah, I was thinking like one way is to discretize it. I mean, another way is maybe use a different way to do like the count-based systems in continuous spaces. But yeah, all this, I'm still thinking about it. If you all know about this, you can let me know. Yeah, then especially the next point is like, how do you know when two states are similar? Because right now the environment we have, the two states are exactly the same. They are just like the coordinates. But in future environments where we have multimodal systems, maybe your visual and your audio like combination together may be different from what is that stored in memory. Then how do we know how similar the states are? So one way I was thinking is using like some form of cosine similarity, or you know, like those, you take two vectors u and v and then you just times together. Yeah, that's like cosine similarity already. This is done in the attention method. Yeah, I mean, that's one way of doing it. Yeah, I think this is probably the best way right now that I can think of. Yeah. So these two here is open questions, okay? Because I really don't know how to do this yet. Yeah. So like, how do we define a goal? Because like, imagine you want to go, like, coordinate systems are easy. Like you want to travel from one point to another point. But how about a more complex task? Like I want to do my homework. So my goal is to do homework. But then in order to do homework, I need to like first retrieve memory from my head about look at the question, retrieve memory in my head, and then write down the answers and stuff like that. So this entire sequence of like actions that you need to do is not that easy to configure, like not that easy to like state it out, and like how to split these goals to sub goals. And also the question is like, you need not only to define the goal, you also need to quantify the goal. So because you need to like say that I need to go from like state A to state B, but if state B is to like write down some words, how do I quantify what is state B, right? So I mean, I have some idea of like how to do it. So like if you have a neural network here, we can actually use the advances in NLP to help. Like you can put your goal in words. Okay, and then out comes like a vector representation. Yeah, so I mean, if you have some way to represent like your goal into a like a numerical state like this, you might be able to define the goal and quantify it using like some form of NLP methods. So that's something that I think can be worked on. I saw quite a lot of Neurips papers doing this kind of approach, using NLP to quantify the goal state in reinforcement learning. So I think this is promising. Yeah. You all have any things to add for this? Because this is actually the last slide for today.
I think I have one related question. So related to defining a goal. So sorry, actually the first question. So when you say you want to have a goal-directed search, right?
Yep.
Sometimes, like for example, in the case of goal, right? You want the goal is you want to win, right? But how do you actually do a goal-oriented search where I feel like intuitively it just feels like it's very abstract. Like it can be anything. A lot of possibility can result in winning, right? So how do you actually do something like a goal-oriented search in this kind of scenario?
Okay, can you give an example of the environment you want to do the goal-directed search in?
Go.
Sorry?
As in the game, go.
Oh, in Go, is it? In the game Go. So, okay, so this is indeed one of the things that I haven't figured out yet. So, like, I'm thinking like, okay, let's talk about tic-tac-toe first. Okay, so I was talking to my prof about this recently also. Like, the goal is to win, right, in tic-tac-toe. And to win is like you need to define a state of winning, right? So like state of winning is like maybe three in a row like that, right? Like goal to win is more territory. Like, so you have a list of goals like that. So right now the method works with only one goal. But what if you have like a set of goals that you can go towards? Then like how do you then use like the goal directed neural network? Like this is your current state. And this is like your goal state. And then you have an action, right? So how do we represent this set of goal states as my goal here? So yeah, that's an open question, because I think there are some situations whereby the goal can be very complicated and it's not just one single goal. So there's some difficulty in expressing all of these goals. I mean, one way of doing this, what I can think of is that you can express all of these goals individually. And then you like maybe have some form of way to apart from just this action here, like maybe you can also have some form of I don't know, feasibility, I don't know, value or something. I'm very reluctant to put the word value here, but I mean, if you have multiple goals like that, you might need to like know like which are the goal states that are more promising and which are not so promising, if you want to use the goal directed approach for this. So I would say that this method is not very well suited for board games. Yeah. As of now, yeah, this method right now more suited for like stuff that humans can do more easily, like navigation, like simple tasks, like you go and get the key, you can do. So basically, it's like point-to-point kind of tasks. I think this method will work quite well. But in terms of like how to strategize for like Cicero the game or like Go, chess, I think humans generally struggle with all this. This system would probably also struggle because this is like trying to mimic like how humans think. So I think for that, more specialized architectures that explore the entire search space, like AlphaZero, would be better suited.
I see. Then just one last comment on the last open question here. How do you split the goals into sub goals? So actually, I've done something, I guess, related in the past. So if you can have something like a knowledge graph, right? Then you can basically a prior knowledge and a structured prior knowledge. Then you can actually based on that to infer. For example, you have a goal as some node on the graph, then you can see how do you go from your initial state to the graph, and you know like what are the intermediate nodes, right? Then you kind of can build a hierarchy on what's the intermediate near-term goal to accomplish to reach the destination.
Actually, that's quite interesting. Yeah, I think a knowledge graph or like semantic graph that has some form of like causal relationships kind of thing might be able to like map a path right from the start to the end state. Yeah, but the problem is that the graph might be quite big. So I don't think it may not be tractable to represent everything in the graph.
Okay. No, as in like the graph itself need not to be very low level, right? So in the past, the example I've done is are you familiar with the air tutor environment?
Say again?
Air tutor environment. So it's like you have an agent, a robot agent in some room, say for example a kitchen, right? Then you want it to do something. For example, you want it to cook a meal.
Okay. Yep.
Then you have, in that scenario, you have a knowledge graph where you know like we mentioned, there's some causal relation on what you need to do first before you do something. So you can build this kind of graph, and in that particular scenario, I don't think it's too big. Yeah, it's just you have a set of equipment or a set of tools, you have a set of ingredients, then you navigate in the room, but you know the navigation need not to be part of the graph, but you have like before you want to cook the egg, you need to crack the egg. Before you crack egg, you need to put the pan on the stove, things like that. So you can, for this kind of environment, I think it's quite feasible to come up with such a graph. Then you can have a hierarchical way to fulfill tasks.
Yeah, definitely. You know, last time there was this stack blocks environment, like put block A on block B, put a blue block on the. Then they also have like some form of relation between the blocks also. Like block A is on top of block B is on top. There's something like that. Then when you do like, I think it was the PPDL or something like that. The planning.
Yeah, that's a classical way.
Yeah. So they also have some form of like semantic graph representing the relation of objects. Are you talking about that kind, or are you talking about a graph of actions?
More like a graph of state. So,
so it's different. It's different from PPDL. Yeah. No, sorry. Graph of states means like you put the pan on the stove.
Yeah.
Then after that, you crack the egg on the pan. So it's a series of states that link each other.
But from one node to another, this is a sub-learning goal because it's not very straightforward how to go from one to another. So you still need to learn.
Understand. Are these states expert defined or learned by themselves?
Yeah, that's a part. So you have to like have a prior knowledge on this.
So it's expertly defined. The graph is already made. Yeah. So I think definitely this is one step in getting there. I mean, I've seen a lot of like works like Beta by I think DeepMind, OpenAI. I think they are doing something with regard to NLP already. So this might be a way to advance this rather than doing the graph. I mean, the graph might be feasible for small environments, but if you expand it more, the number of connections between the possible nodes is quite a lot.
But you're saying you want to learn this kind of relation from scratch.
Yeah. So I don't really know how best to solve this. So right now, what I can say is that my goal is given, but these are very interesting things that you brought up. Yeah. So if a knowledge graph can do it, I'm in for the knowledge graph. So I'm not limited in the options that I'm exploring in terms of like how to do this sub goals thing. I think as long as it works, we can use it. Yeah, but the only condition I have is that you must be able to change the list of sub goals based on your environment changing.
Yeah, that's the part. Actually,
so the mechanism must basically account for
that. But it can be, you can have a robust graph, right? Because all those causal relationship is quite general, regardless of in which case you have to have like this a very high level general. You can call it a rule or whatever, like the causal relation. You have to have something happen first before that, and it's regardless of what kind of environment you're in, right? As long as it's this the goal is of this nature, then you have to abide to a certain rule, right?
Yeah, so what I'm thinking is maybe the action graph may not be a specific kind of action, but can be broad actions. Like can put object X onto this object Y, that kind of thing.
Oh, you are still thinking of the action graph. No,
I mean, if you want to talk about the action graph, yeah.
Actually, I'm thinking from the state perspective. So I think it's possible to make it more general. So
I mean, if you think of a meta graph that is very general, even for the states graph, then I think that will work. Because if your states change, you can still use the meta graph.
Yeah, I think that's why I mean,
Yeah, thanks for sharing. Yeah. So this one, as I said, I haven't worked on all this. These are just like things that will pose difficulties for like using this for different environments, because currently most R environments don't really have this goal. Like they only have reward functions. So you need to quantify the goal, which is easy like for a navigation scenario. But like stuff like walking, I'm still thinking of how to define the goal, because maybe the goal is you need to travel from one point to another point. But for walking, there's an additional difficulty in that you have to take the kinematic states of your joints, the velocity and the positions, which can be different. So you need to, your state not just only the X and Y axis or the Z axis, you also need to take into account all the velocity, basically all the Mojoko kind of dynamics, also part of the state. So yeah, that will be a bit difficult. Okay, if not, yeah, anyone else got questions? If not, I'll be ending the sharing here. All right, not thanks for coming.
Thank you, Changmin.
Let me just find a way to end the recording.